So the key to graphing is to make an XY table, just like all other functions, and plug in convenient numbers that work for you. Example, if they ask you to graph log base 3 of x, easy numbers to plug in would be 1, 3, and 9. Because the domain values would give us the output values, the y values of 0, 1, and 2. Okay, could we plug in 0 or negative numbers? No, it doesn't work. Because if you think about plugging in negative numbers right here, like 3 to what power gives you a negative number? It doesn't exist. Even if you go positive or negative numbers, it will not give you an output that's negative. And what happens as it approaches 0? Well, you could be plugging in nice numbers like 1/3, 1/9, 1/27. Your output will be -1, -2, -3. Now, I'll be honest with you, that is stinking confusing, right? Let's take a look at this function y equals log base 3 of x. Oh, that's too big. Y equals log base 3 of x. So instead of, first of all, does this have an h or k value? No. So we know we're not moving left, right. We're not moving up, down. So we know the h and k. Now, instead of trying to come up with the values that work for log base 3 of x, instead of that, how about this? What if we think about the inverse of log base 3 of x? What is the inverse of log base 3 of x? It's simply, let me do this. It's simply y equals 3 to the x. So notice I covered up the log and it kind of looks like an exponential growth function. And since we know that the inverse of a log is an exponential growth function, I could simply cover up the log and pretend that it says y equals 3 to the x. Does that make sense? Now, pretending that this is not a logarithmic function, pretending that it's y equals 3 to the x, how would we get coordinates for that? We're going to use -3, -2, -1, 0, 1, 2, right? Let's go for an easy input, like 0. 3 to the 0 gives me 1. The next number, since this is what kind of function? Growth or decay? Growth. The next number is going to be a what? The next output. It's going to be a 3, and the next output? 9. Come on, people. Going backwards, we'd have a 1/3, a 1/9, and we know it's getting smaller and smaller and smaller, closer, infinitely closer to 0. Okay, so let me, I could plot these points, but what's the point of that? These are the points to the exponential growth function, not to my exponential decay function. I mean, exponential decay, not to my logarithmic function. I'm sorry, said exponential decay. So we have the coordinates to the growth function, but we really want the logarithmic function. Now, what do we know about this guy and this guy? They are inverses of each other. So if these are the coordinates of y equals 3 to the x, what are my coordinates going to be to log base 3 of x? The coordinates are simply going to be switched. So my actual coordinates, instead of -2 and 1/9, it's going to be 1/9 and -2. Instead of -1 and 1/3, it's going to be 1/3 and -1. Instead of 0 and 1, it's going to be 1 and 0. Instead of 1 and 3, it's going to be 3 and 1. Instead of 2 and 9, it's going to be 9 and 2. Does that make sense? Okay, let me repeat what I just did. First of all, if they give you log y equals log base 3 of x, it's kind of hard to come up with coordinates for that. So what we're going to do is cover up the log base 3. We're going to cover up the log, and we're only going to focus in on the little 3 to the x. So it looks like the function y equals 3 to the x. That is technically the inverse, right? So we're going to graph, or we're going to come up with the coordinates of y equals 3 to the x. And we get this xy table, we get these coordinates. Now we know that these are the coordinates to the exponential growth function, but not to the logarithmic function that we want. But we know that they're inverses of each other, and we know that inverse functions simply are switching x and y if you have coordinates. So we switch the x and the y values, and then we actually get our true coordinates to the log base 3 of x. So you take these guys, take the -2 and the 1/9 and switch them. Take the 0 and the 1 and switch them. Take the 1 and the 3 and switch them. And you get these new coordinates, and now you're able to graph. Okay? So graphing these guys, you'd have 0, 1, which is right here. You'd have 3, 1. No, I'm sorry, I said 0, 1. It should have been 1, 0. 1, 0, which is right here. Then we have 3, 1. We have 9, 2. And if we go in this direction, 1/3 and -1. 1/3 on the x. That means you would go 1/3 of the way, not even halfway out. And what do we get as an output for 1/3? -1. So we're right here. And then what's the next one up? It's 1/9 and what? 1/9 and what? -2. The next coordinate, 1/9 and -2. So 1/9 is even closer. So we know that it's going to continue to get infinitely closer to the y-axis, to the x equals 0 value. But it'll never actually touch. It'll just infinitely approach. And there's your graph. So down here in our notes, I explained the trick that I did, which is just cover up log. So if you cover up log base, or cover up log, it's going to look like y equals 3 to the x. That's what it looks like. Then you make an xy table for that exponential growth function, and then you switch the x and y values, and then you could graph. But of course, if you had an h and k shift, you have to shift your final coordinates according to h and k. So let's try this one up here that does have an h and k shift. What's the first step to graphing any function? Identify h and k. So what is h and what is k? -3, +1. So you're really going to be going 3 to the left, 3 in the negative direction, and 1 up after you get your final coordinates. Okay? So once you identify h and k, you could ignore h and k, correct? Yes? Okay, now from here, we're going to try to graph log base 2 of x. I need an xy table for log base 2 of x. But I know that that could be really confusing. So how about this? I'm going to cover up the log part, and that way I could see the equation y equals the base 2 to the x power, right? So it'll look like an exponential growth function. Y equals 2 to the x. As a matter of fact, let's write that over here. Y equals 2 to the x. And we're going to make an xy table for y equals 2 to the x. Once I get these coordinates, then I could switch them to get my logarithmic coordinates. Of course, it's always very important to use consecutive integer inputs in order. Let's plug in a number into the y equals 2 to the x power. Let's plug in 0. When I plug in 0, right there, I get out what? 1. Okay, now at that point, I could just modify the output 1. How am I going to modify this output 1? By looking at the base. I know it's a growth. How is it growing? It's growing by 2. So the next one's going to be what? 2. The next one? 4. The next one? 8. It's growing by 2. You're multiplying by 2. In the opposite direction, instead of growing by 2, you're going to be dividing by 2. You're going to be multiplying by half. So you get 1/2, you get 1/4, you get 1/8, and it keeps getting smaller and smaller, infinitely approaching 0. Now, normally I would graph these if it were the exponential growth function, but we know it's not the exponential growth function. It is the exponential, or the logarithmic function. So I need my coordinates for my logarithm right here. So I'm going to take these guys and switch them. So instead of -3 and 1/8, I'm going to plug in 1/8 and -3. 1/8 1/8 and -3. The next one, 1/4 and -2. The next one, 1/2 and -1. The next one would be 1 and 0, and then 2 and 1, and then 4 and 2, and then 8 and 3. So we have all the coordinates that we actually need for the logarithmic function log base 2 of x. Those are the coordinates, the actual coordinates. Now let me graph these coordinates. Let me go with 1, 0. 1 on the x, 0 on the y. There it is. Let me go with 2, 1. Let me go with 4, 2. Go with the next one, 8, 3. And now the more interesting ones, 1/2 and -1. So if I go halfway out from the origin and then go to -1, here's the origin, go halfway out and then -1, I want to get that dot right there. And then the next one is 1/4 and -2. So if I go 1/4 of the way out and -2, I'll be right here. And we already get the idea that it's going to get infinitely closer to the x equals 0 line, but never actually touch. It infinitely gets closer to the y-axis, but never actually touches. I could draw my asymptote already, like if it's actually touching, even though I know it never actually touches. However, this is still not my final graph. What I still need to do is shift everything according to h and k. So my h was -3, my k was +1. So I need to take all of these coordinates and move them 3 to the left and 1 up. Let me start with the asymptote right here. If I move it 3 to the left and 1 up, it's going to be the same asymptote, just over here. Does that make sense? Let me take all these other coordinates and move them 3 to the left and 1 up. These nice ones like this one, 1, 2, 3, and 1 up. Whoa, right there. And then the next one, 1, 2, 3, and 1 up. And then you move them all over that way. And you have your actual graph of your logarithmic function. Now, if you happen to have mistakenly drawn this red one, the original one, without the h and k, just put 2 x's on there so I'll know that that's not the graph you were talking about. And now let's also go to something more entertaining, like the domain and range. The domain of this guy, of this blue logarithmic function with this h and k shift, the domain of this blue logarithmic function is x is what? X is, does it go left and right forever? No, it doesn't. Does it go to the right forever? For sure, yeah, it goes to the right forever. Does it go to the left forever? No, it curves down, and it actually infinitely approaches a certain value. What is that value? -3. So you need your x to be what? Less than -3 or greater than -3? Greater than -3. So your domain is greater than -3 right there. Now your range, that's your y values. Your range or your y values, y is what? This blue line, does it go down forever? Yes. Does it go up forever? Yes. Even though it's curving, it's still going to continue to rise. So your range in this case is all real numbers for this logarithmic function. And we could even